Could always be fun. Anyway, we are currently looking at filling out some stuff after method of undetermined coefficients and variation of parameters. Nice. Looked at finding, what was it, second order linear differential equations. So we have somewhere a copy of the oh, come on. Switch to tab, there we go. No, it's not what I wanted. Punks. So close. Definitely not what I wanted, but nonetheless. Okay, so this is the William Trench book we were looking at before. That's going to be inefficient. Table of contents, someone around page 20. We just keep backing off here. Okay, so we had variation of parameters, reduction of order. Again, that reduction of order is to find the second solution given another solution. Very technical. So why do we do reduction of order? So there's the possibility of an easy solution and one that you could just kind of like grasp out of thin air and be like, you know what? I think that this is going to be possibly a linear function or something like that, which may seem kind of trivial under some differential equations, but in other cases it could be not obvious that like what the other solution is going to be. So we say, okay, we're going to do, given some potentially easy solution, we're going to do reduction of order in order to find the other one, which is not obvious. That is not where my mouse is. I need to stop grabbing my phone. And I'd also like to potentially increase the size here. Yeah, something like that. Okay. So there's the possibility of an easy solution, or I just had like a brainwave in order to figure out like why the other, you know, you'd have one solution. You could have like an alternate representation. Or there is the possibility that you could have more solution types. Given the DE that you have. So whereas it is possible that you're like, oh, well, it is not always true that a differential equation, second order differential equation, only has these two solutions that you found. It is true that it will have two linearly independent solutions but those are not guaranteed to be the only ones. So uniqueness, I think, tends to fail us sometimes. Not always, but under some strict conditions, uniqueness tends to not 100% work every single time. Especially if the system is not, extremely well defined or developed. There's the possibility, but most of the time that's not the case. Like the ones that we do in differential equations are usually fairly nice, so they only have these solutions that we gave you. And it could be as simple as saying, well, there's a trivial solution where y is equal to a, some constant. And then go from there, you can find a second solution. Okay, so we do a bunch of applications, which includes springs, RLC circuits, motion under force. Now this is also one of the age-old questions. Do we do Laplace transforms or do we do series first? I think our tendency in my classes has always been to teach power series first. Nope, sorry. To teach Laplace transform first and then power series. But I don't know how to decide, really, apart from just flipping a coin, because they are technically independent of each other in terms of, like, what you would be assessing on an exam or something like that. You don't have to technically know, how to do Laplace transforms in order to do power series or vice versa. Okay, so that's not telling me. There we go, 260. That's not the right account. Oops, man. Every time, man. Playing yourself. Alright, oh no, we did infinite series first, and then Laplace transforms. Okay. So it's the same as, well, okay. This was out of the trench book, so yeah, that makes sense. I'm not sure how Boyce and Prima did it, but it's probably the same. Alright, so immediately after second-order linear differential equations, they do matrices, which again, we've already done. Reduction of linear differential equations into first-order equations, systems of first-order equations. So again, we talked about that earlier on. Graphical methods, so like we did that way early. I'm just looking at the Shams see what their order is here. So numerical methods. Ooh, Adams, Bashforth, and Moulton method. I don't know that one. Milne method. I don't know that one either. I'm not sure it's worthwhile compared to, no offense, compared to Runge-Kutta, but... Start with your differential equation. Y prime is equal to some function of x and y. So in this case, they're just using the simple one, y prime is equal to y minus x. And given some starting point, for instance 0, 2, on the interval 0 to 1 with h of 0.1, find the additional starting values to be as follows. Y prime is equal to y0 minus x0, so that's 2 minus 0, which is 2. Y1 prime is going to be y1 minus x1. So we go from now I don't know what they're doing here. That's weird. Oh, okay, there we go. Using table 19.3. That's probably my issue. It's identical to Runge-Kutta for the first several. You use the Runge-Kutta method and consider that y prime at each of those individual. Look, this is crazy. All right, we're not we're not going into that. Well, anyway. Values of y0, y1, y2, y3, and their derivatives in Milne's method are exactly the same as problem 19.7. But then, oh man, that's good times. Anyway, numerical systems for you. I know, right? I decided to put up goals. So, follower milestone is a nice easy one because it doesn't like require anything of people other than clicking a button and getting occasional notifications. And you can even turn them off if you get annoyed. So I do want to thank all of my followers out there. Thank you so much for stopping in and saying hi, and you're awesome people. Thank you. Mm-hmm. So yeah, they go into Laplace first. Interesting. Again, I don't think it matters, because there's nothing that's going to be dependent upon the other. Matrices after, then no, is that series? Yeah, linear differential equations with variable coefficients. So that's when they start getting into series, power series. Man, chapter 26 must have been like 3 pages long. Yeah, pretty much. Six, 8. Alright, so... I think we wanted to... Yeah, okay. So we want to do Laplace transforms first. Because power series really starts then going into variable coefficients, whereas Laplace transform still uses constant coefficient. Yeah. Really? Continue numbering? Is that a thing? It is a thing. Continue bulleted list. Numbered. About the exact same thing as above. Restart numbering. Okay, nope. Continue previous numbering, but then restart. Boo. Oh, no, don't do that. Alright. Good enough. Okay, so first thing we want to do is talk about the definition by using the integral definition. And like, why would we even do this in the first place? get the properties off of that. Once again, if there is anyone in chat actually looking for math help, feel free and ask. Type it in the chat, or we can go to that's not the one. We can hop into Discord here as well and get Penn Center's math help channel. Probably should actually start Discord. It's fine. It's fine. Alright, so I want to talk about the purpose and the properties of Laplace transforms, which then means like also solve these integrals that have secondary variables. So the ones that have, for instance, the Laplace transform has integral from 0 to infinity of e to the negative st of f of t dt, and figuring out for what values of s an integral will converge or diverge. So that's kind of the crux of trying to figure out what's going on with Laplace transforms, is figuring out how all this other stuff goes. Hey, how's it going, Justice? We are doing some curriculum writing for a differential equations class that I'm planning on teaching over this summer, right here on Twitch. So if you have anybody who might be interested, let me know. Send them my way. We'll try and figure it out. There's not really a prerequisite, but at the same time, the mathematical chops that someone needs to have is probably going to be like doing okay in Calculus 2, that level type stuff. So if you know anybody, you can send them our way and we can give it a shot, see how it goes. Otherwise, you know, we've got usually Tuesday night streams, lately anyway, has been devoted to, yes, has been devoted to doing mathematics, and typically I've got a whiteboard set up here that I can switch to and write on, and tablets. We've done a few art streams as well, attempting to make some new emotes, which are like not very good, but you know, they're my own, so that's sometimes that's all it takes. There we go. Oh no. There we go. Okay. We're getting a little fuzzy, maybe. So yeah, streams been going all right so far. I haven't really done much, to be fair, but you know, hanging in there. Up to anything interesting today? That goes for anybody. Presentation tomorrow on your research? Yeah, nice. Paper and a math problem. Okay. Yep. Nice. I still need to get back into working on some Python stuff and doing wherever it went. Euler project. See if I can increase my programming ability with Python specifically, because yeah, it's been forever. Alternatively, we might be able to figure something out with Lean. Okay. So we want to find the Laplace transforms and then invert the Laplace transforms of just functions by themselves. Kind of make it sort of divorced away from differential equations itself. Just practice a little bit, see how that goes. And then we want to be able to then apply that Alright, that's also going to include somewhere in here. I think I want to do that there. It's maybe a little weird something, but yeah, whatever. Okay, so we got integral, definition, purpose. Really, it's kind of breaking about here, though. it's like doing it, right? Just figuring out how to do stuff with it. That'll be fine. Inverting Laplace transforms then is also going to include like all sorts of function types. It's going to be ridiculous. And then methods which include completing the square for a lot of these. And fractional decomposition. What do we call that? Partial fraction decomposition. There we go. Remember that from Calc 2? Woo! Convolution is going to include both the multiplicative and additive. I think most people put it in that order because the additive stuff is going to be a little bit harder to work with. Right, shifting something ends up messing up everything. Like changing around how the inside of a fraction goes. Sometimes it's a functional. I mean, it's a shift, but function transformation, and on the other end, it's a multiplicative factor when you're inside the Laplace transforms. And then wait a sec. Yeah, we'll go back here. Okay, so with process, then we'll do all the finding and inverting. thing. And it doesn't matter what actual order these have, it can go out to whatever order differential equation you want, because you're just going to create a polynomial, but has to have constant coefficients. It's getting pretty dark out. Alright. No, should hope so. It's 1250, but or 1050. I do math, I promise. Okay, we want this to be a superscript, not that. Superscript. Okay. Homogeneous, inhomogeneous doesn't really matter because it's just gonna fix itself real fast. We don't even need to set aside a, like, separate thing. Don't even necessarily need to set aside a separate thing on this one for applications, because it's kind of all the same as all the rest of the differential equations we've been doing. This is interesting. Shams goes into solutions of linear systems by using Laplace transforms, and we start getting into like using both capital U and capital V as function names. I don't think I've ever done that before. That's crazy. I like it, but it looks slightly daunting. Simultaneous linear equations, find the solutions, then just reverse it, come back to inverting the Laplace transform to get solutions or solutions to the system. There we go. Using matrix methods, yeah, we already got that. Yeah, that's kind of it. If we think of anything later, we just add it back in. Alright, so series representation. In this particular case, we're really focusing just on power series. and we can talk a little bit, just real quick, on like what Taylor series is and how it worked in Calc 2, but at the same time, we're not going to be using that in differential equations for the most part, because what we're going to be concentrating on is just letting the constant coefficients be whatever they need to be in order to make this work. So we're going to talk about this in the context of Calc 2, and then we're going to talk about how we need to be expansive or inclusive for this, and not limit ourselves by just saying, oh, well, we're going to do a Taylor series, obviously. It may not be the best case, or it may not even work entirely. Nah. Okay. So we're going to use power series representations for solutions to differential equations by then, right, find the derivative or derivatives of the series as a whole. So I'm going to set this up as a recurrence relation. There are going to be potentially multiple methods to arrive at any particular recurrence relation. So there's like two main ways that I'll do it, and that is by gathering like terms. What was it? We shift the limits on the sums at the beginning, or we alter the terms that are in each sequence. Something like that. So, alter the limits of the sums, or Right, evaluate some terms until they now have the same number of terms in them. Which is technically infinite, but... we'll see how that goes. We can throw this in here too, real quick. Right, what's an analytic function? In theory, if pen's already gone, then there's a good chance that we've already discussed what are analytic functions. If not, I'm no expert, but my students might be. Woo! Okay. Oh, nuts. I just realized I missed, there was some free legal advice at the library today. I missed it. Completely spaced on it. Could have gotten advice on how exactly to set up my business entity. Like keeping our assets away from company assets and all that stuff. Woo. How would I want to do that? Oh well, I'll wait until next Tuesday, I guess. Nope. One after that. Yeah, there we go. Okay. If something is not an ordinary point itself, then we can do a function transformation and shift it until it is an ordinary point, or until it's located at x equals 0. Okay. Alright, so doing stuff at regular singular points, I think, is going to be one of those things that's typically really hard, or at least most people don't bother with it. In an ordinary differential equations class, they'll either wait until masters or potentially not do them at all. So I think I would like to bring it up at least as like a further extension in terms of like how we could potentially go further, push our particular differential equations. And see if we can't do, like, you know, something special, essentially. Okay. I think I'm gonna take a quick walk downstairs. Trade out my tea. Get this thing rinsed out and all that. And, you know, just generally speaking, stretch, whatnot. So I would encourage everybody else to do the same. I will be back in 3 minutes, thereabouts. And thank you for sticking around. This is Obi-Wan Pez for N-Simplex Pachinko. I'm not leaving for the night. I'm not leaving. I'm just going on break. What am I doing? All right. Here we go. 3 minutes. Thank you. Hey everybody, sorry about that. Took a little longer than expected, but nonetheless. Needed to fix myself a little snack here. So we've got some assorted crackers with a Wensleydale cheese. This is the first time I've actually had this. It's fairly local. Wensleydale is a town that's in the Yorkshire Dales, which, as far as I understand it, is just like kind of a general term for the northern towns, villages, and like, you know, the hills of the northern, I believe, Yorkshire area. So we went to a place that has it's an old, like, noble person's house, basically, that has been converted into pseudo theme park. Like, it's just basically somebody's, the grounds of their house. Alright, I don't know how well anybody can see it, but so Wensleydale itself is a kind of mid, I'd say, hardness cheese. It's fairly crumbly, as you might be able to see there, because it just, like, absolutely fell apart. It's got a bunch of wax in it because I am terrible at cutting. But yeah, so we got a whole bunch of, like, crumbly bits. It's definitely, I think it's technically in the hard cheeses, because it doesn't, like, melt together like brie or something like that, especially at room temperature. But I don't really know much about it other than where it comes from. And there was once a Wallace and Gromit episode where Wallace meets a woman, and, like, one of his best known traits is that he is absolutely insanely crazy for cheese. And at some point he asks if she would like, you know, she would like some cheese, and she was like, "Oh no, I don't really like it." And he and Gromit exchange glances, and he's like cheddar? Yeah, well, probably not cheddar, but, you know, come up with like 10 different names of cheeses, and she's like, "Nope." He's like, "Not even Wensleydale?" So I always thought that it was a bit milder, but I'm not getting that. Like, it feels to me like Wensleydale's a bit stronger of a cheese. I don't know if that's true or what. Maybe it's just like an easier kind of cheese to eat, instead of like brie or several of the other ones. You kind of have to have an acquired taste because it's a little more bitter. Or it pairs well with wines, not really necessarily just eating it by itself. Yeah, I'd say it's stronger than cheddar or most other cheeses like that. It's more like a sharp cheddar to like the really sharp cheddar. And this week, oh, that's why. This week's hashtag not sponsored is Deya, D-E-Y-A, The Sun Drips Honey, double IPA. Fresh double IPA for spring. Pineapple, mango, and some funky white grape taking a long walk on your palate. Yep. So at 8%, this is rather strong. Best before. Oh yeah, September. We're good. It is fairly intense. It's got the same piney notes that an IPA has, but at the same time, there's a lot of fruit in this. When I was downstairs, I took a little sip. I think the mango is what was throwing me off before I checked the label. I saw IPA and I was expecting, like, you know, grapefruity, sour, bitter, and there's none of that. There's like the very tail end of it. You got a little bit of the piney bitter, but very fruit forward. Okay. So this goes into Laplace transforms, series representations. These have ordinary points. Again, I think I want to touch on singular, but just barely. Oh, and then we want to do linearization. Was another one that we did. I don't actually necessarily see it here. It is supposed to be non-linear systems, so actually it may not even be this particular one. Let's see if we got the other book in here too. Maybe not. Excuse me. Nope, 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 nope. Got all these things that were still open, like way in the back of my Firefox, you know, tertiary window or something like that, that were all from my old job. So I clicked on something and closed it, and then it just decided, oh, you want to log in? Like, nope. I really do not want to log in. Okay. So let's... Digital Commons. I think we want like the almost exact same thing. but we want the one that's our elementary differential equations with the other one. So elementary differential equations with boundary value problems. Yeah, trench, right. With boundary value problems. There we go. Alright. I mean, we could download it, but... Is this one downloaded or is it online? It's online, so we can get the other one online. It's fine. Can we just open it? Yeah, there we go. Really? He doesn't have it. He does Fourier solutions for partial differential equations. That would also be an interesting thing to try touching on a little bit. And boundary value problems and Fourier expansions. So... yeah, series representations that'll be used to solve partial differential equations. Oh. Okay. So, sort of. The things that we did in 15 weeks included nearly every major topic group, but did not necessarily cover every subject within those topics. Like a lot of the stuff in chapter 5, we're talking about like solving for homogeneous and non-homogeneous linear equations, like that's going to come out in discussion basically. It doesn't have to be a separate like problem type that we have to talk about at length. It's just going to be like, well, what happens if it's not 0? And let's try this other function. And somebody's going to look at it and be like, well, yeah, you can just solve that thing. Basically, it doesn't change anything. It just, yeah. Well, not second order. First order. First order, when you go from homogeneous to non-homogeneous, it's just like, well, that doesn't really do anything. So we won't be too worried about it. When we talk about second order, that's when it starts being a little bit weird, because you have to have, you know, whatever order you're working with, you have to have that many linearly independent solutions. But that's for the homogeneous, like the way the system is set up. So the homogeneous solution matters, and then the non-homogeneous solution is going to be like what happens when you introduce a forcing function. The system normally behaves this way, but then you're messing it up, so it's going to have this added effect to it. Right, undetermined coefficients is easy enough to figure out. The only thing that they do extra, they split it up into 1 and 2, is because under 1, you're just saying, you know, what are the undetermined coefficients? Oh, you look at the function type that's over there and you give me another function type that's exactly the same, just you don't know what the variable is. The undetermined coefficients 2 is what happens when your functions are, your homogeneous and non-homogeneous functions match in some way, shape, or form. Yep, pretty much. Dude, we had a rhythm. Get with the program. So yeah, actually, there's a couple of sections in here that I would like... Nope. There's a couple of topics in here that I would like to talk about, but at the same time, I don't think it's actually... I mean, you're going to talk about it in terms of partial differential equations, those who take partial differential equations. So, like, I don't necessarily want to bog it down, but I do think that at least discussing how nonlinear differential equations work and linearizing them is something that we did in Boyce and DePrima, which I don't see in Trench. And I think it's actually pretty worthwhile, because if you're looking at this really complex system, you could just be like, well, I don't know what this is, but if we zoom in on any one singular point anywhere in the entire differential equation, then the stuff that's immediately surrounding it acts just like when you're talking about the area immediately surrounding a 0 for like a polynomial function, right? The behavior depends on what's going on around that particular 0. Like, the rest of the equation doesn't really matter. It's just what's happening with this particular thing. So, in polynomials, we look at the multiplicity, and then we look at what's the sign of the rest of the function before and after this particular singular, or this particular 0. In a differential equation, specifically nonlinear, you could say around this one singular point, everything tends toward, everything relating to this point tends towards 0, everything else around it can be basically simplified because, you know, any minor change that you're making, as long as you're staying within a certain radius, and neighborhoods is going to be an interesting topic in here. As long as you're staying within the appropriate neighborhood, like, the behavior of this neighborhood is dominated by the behavior of the singularity. Singular point, not singularity. And then any deviation from that is going to be based on the sum total of the entire rest of the differential equation, but it's not going to be a huge difference within a reasonable local region. Yeah, less than epsilon. Yeah, Lorentz system. Yeah, not so much. We can talk about it, but I certainly do not have any expertise in Lorentz systems. Apart from, I've seen it, and I have occasionally, like, I didn't do any work with it, but we did very briefly. I shouldn't say very briefly. I took an entire class in nonlinear differential equations, but a lot of it was the same as with partial differential equations. Here's some cool stuff. Now we're going to move on to the entire 2/3 of the class that's based on numerical methods. Great. You know what? I have not. But hey. Yep. Beat me to it. That one's a PDF, though. .ro. Oh, that's Romania. Interesting. Second edition. Oh yeah, CRC Press. I interact with him occasionally on, I don't know if it's Twitter or Facebook, but one of the two. He's cool. Yeah, I'll have to look at this later. Yeah, I don't even know what I did in order to get this. I just kind of went with, like, pretzel, clicked on, what did I do? I clicked on surprise me. Which, like, this is not actually that surprising, I guess, but I like it, so. So yeah, our Boyce and DePrima book covered a whole bunch of, you know what? That is a good question because I don't know that I have anything spicy in the house right now. um, it was, I don't have any right now, but it was Grillo's, yeah. That's not actually supposed to be an option right now, because my stream title doesn't have the words hot in it. Or maybe tags. Something like that. Aniakui! Thank you very much for the follow. My name is Obi-Wan Piz. This is N Simplex Pachinko. Das the in hoist? Yeah, okay, now I gotta go find a weight. Thanks, Zach. I mean, good news, right? At least you're keeping me fit. Oh, this'll do. Alright, so this is our day bag, which has been filled with a whole bunch of stuff. But you know what? I'll even add to it. We'll up the ante here a little bit, because I'm going to be using two hands, so it's fine. We will add the other books we have here. Numerical Solution of Ordinary and Partial Differential Equations by Fox, Edwards's for Fermat's Last Theorem, Courant's Dirichlet's Principle, Shield's Linear Algebra, and Fermi's Elementary Particles. So we will add that to the bag. That'll get us a good extra 10 pounds at least. So, yeah, I'll even squat for you. So we'll just do this about, I don't know, 50 times or something like that. That's good. We're starting to slow down a bit. That's some muscle groups I haven't used in a while. 35. Alright, we'll do 40 there, and then we'll go just regular curls for, let's do 10 each as a penalty. Goodness. Woo! Good times. Alright, Zach, thank you for keeping me healthy and alive. It's a group effort. Oh. Yep. Push-ups, I'm terrible. Like, I can't really do more than about 10 or 15 at a time. And like, I've never been able to do more than 10 or 15 at a time. So when it came to like, let's do the Presidential Fitness Award in school, I was just like, man, I'm out. Could do the rest of it, or I couldn't do pull-ups either. I've never been able to do proper pull-ups. I can do tricep pull-ups. So you pull yourself up this way, I could do about 4, but like this way I could get maybe 2, and it was just never. My biceps have always been kind of underdeveloped, I guess. I don't know. Probably just doing the wrong exercises. It's fine. I see your threat. My OB account has 260,000 simplices at the moment. Oop. Nope, not that. Yeah, I was running cross country in junior high, and 7th and 8th grade, just for me. Our school was a little bit weird. We had 6 towns, which all sent everybody to the central town for middle and high school. And middle school, though, for us wasn't actually middle school. It was junior high, and it was only 7-8. It was middle school for them because their kids were 6, 7, and 8. So it's just so messed up. All the sending towns had their own 6th grade system for a real long time. And when my brother started going to middle school, I can't remember what year he was in when he was first there. It might have been 8th grade, actually. But yeah, they started doing everybody 6, 7, and 8. So all the sending towns only went through 5th. And it kind of standardized everybody across the board. But anyway, so yeah, I went to junior high, and my cross-country coach was, I don't even know who she was in terms of like where in the school she worked. I think it was English, but I never had her. She said, okay, we're going to do crunches. And I'm like, all right, what's that? Like, I'd never even heard of it. And she was like, well, it's a sit-up, but you're really just doing the effective part of the sit-up. I was like, all right, cool. So she had us do, eventually, what it came out to be was we do like 10 sit-ups straight up, or 10 crunches straight up, and then 5 to the left and 5 to the right. And 10 more straight up, and then 5 to the left and 5 to the right. And like day 2 rolls around, and I'm just like, oh, because I don't do this. Like, I don't use my abs that much. We did 5 sets, and so that was 100 crunches. Granted, you know, you're spreading it out a bit, but yeah, we did 100 crunches on like day 1, and then by the end of the semester, I had incredibly strong 6-pack abs underneath a good, you know, little layer. I was actually pretty skinny back then, but one of my friends, I was like, yeah, you could punch me in the stomach, it'll be fine. And she was like, I don't know, really? I'm like, no, seriously, go for it. And so she was just like, all right, wham, like that. And she was like, ow. This was the same girl who, in high school, we were playing indoor soccer. And I think it was like nuclear indoor soccer. So like you could kick it off the wall and catch it and then start dribbling it. 1 point for a basket, 2 to get it in like the little pug nets, which are, 2.5, 3 feet tall, 3 feet, 4 feet wide soccer nets. So 1 point to get it in there, 2 points if you kick it in the net. And we were getting really into it, and the ball goes flying off there. It comes off the wall, comes right to me, and I'm like, I got this. And so I do like a spinning round kick. So like I flatten out my foot and just go whack like that, and it goes bam right into her face. I was like, okay. Coach, I'm gonna sit. He's just like, yeah. Okay, all right. That was just regular gym class. If you didn't know it about me, I'm a little bit of a tryhard. No. So the other thing that was kind of fun about our gym classes was in freshman and sophomore year, you just had gym class. Like, that was it. And it was mandatory, and everybody had to take it. So you get a mixed bag of, like, whoever fits into that particular slot. When you get into junior year, you were able to select which particular gym class you wanted. So I was like, I want to do team sports and outdoor sports. And my girlfriend at the time was just like, why? Like, you should be trying to do as little work as possible for this. I'm like, no, you get like fit and stuff. It's more fun this way. She was like, all right, whatever. So, she did lifetime sports, which was like learning how to play ping pong and learning how to, do some other stuff and walking and like very low impact. I'm like, I do not want to do this. But to each their own. Our outdoor sports, outdoor education, yeah. Our outdoor education class did a whole bunch of like rock climbing and team building activities, and then we went and climbed at Pawtuckaway State Park, which is, we went rock climbing on rock in Pawtuckaway State Park, and I was like, I know this place. This is so great. We're gonna walk in the exact same place that I have been climbing since I was 5. We get to the exact same rock slab that my dad like encouraged me up when I was 8 I didn't actually, to be fair, I didn't actually start climbing until I was like 7-ish. But my dad was like, hey, if you make it to the top, I will buy you your own climbing shoes. And like after a few times of being like, no, I'm not doing this, I think I was 8. And, you know, I'd only ever made it to like here before, you know, within arm's reach of my father. And he was like, offer still stands. And I was just like, made it all the way up. Never got my shoes until I was moving out of the house, and I was like, you know what? You have not used these in 10 years. I'm taking them. So I took his climbing shoes. I had them until last year. The guy at the climbing gym was like, oh, these look so great. They're like super retro and all this stuff. I'm like, yeah, well, I mean, they're kind of falling apart, but finally the soles gave out. So they sheared off the bottom, and underneath is like just wood. I mean, they're like 1980s rock climbing shoes. But anyway, yeah, so our outdoor education class went to the exact same place that I had been climbing since I was, you know, okay, 7 or 8. But this is me at 17. I'm like, this is you guys have got to try this. Go over here. Hey, I know all the holds up this one. It's in Raymond, New Hampshire. It's not somewhere that like most people ended up like ever finding. It's really back in the backwoods of Pawtuckaway State Park. When I was about 5, we started going and just like watching my dad climb with a bunch of friends, so you can tell how interesting that was. But we'd also got like the culture of the climbing and understanding, like, you know, somebody's gonna yell rock, you better cover your head. And you know, we kind of grew up with the culture of climbing. But yeah, it was we were there for one of our first couple of times, and there had been some heavy rains, so one of the areas was like this dip, and it was completely flooded out, and there was a pickup truck that was about halfway through it. And like 3 20-something-year-olds who were all sitting on top of it, like we're just like, we're just gonna park over here. Like, we'll find a way around, it's fine. But yeah, we so I went there with my outdoor ed class and taught them, like, you know, told them all where the best places were to put their hands and feet and stuff like that, and they're all like, what the hell? How do you know this? Like, I've been coming here for 10 years practically. But yeah, that was a great place. I don't know, I guess I haven't looked it up, right? Like how much climbing is still done there. There was so the section that we were on was called Pete's Tree, and like it was probably 6 belay spots across a granite slab, and like varying difficulties. So you could try all of them and see how it went. And then like a few hundred yards back from there, there was another place that was like chimney formation. So you could get yourself wedged in and then work your way up, climbing that way or up that way. So it was all top roping that we were doing, and like I've never really felt the interest or need to try lead climbing. Kind of freaks me out. But they actually do that here. There's a place that's like couple dozen miles or something, called Brimham Rocks. And like if you've ever, it is, yeah, that's the one. No, jerks. Alright, get rid of all this crap in the URL. There we go. So the National Trust sites are like the places to go. There's all sorts of cool stuff to see. There's a one called Fountains Abbey, which is, I mean, an old monastery where, yeah, Abbey, right? Because slightly different. Anyway, but it's a monastery and abbey. So there were monks who were living in this place. There's like half of it is destroyed these days, but it's very interesting. They also have an underground, I mean, not like all the way underground, but like the foundation is dug into the ground a bit, and there's a maybe 12-foot high and like 100-foot long area where you can walk through, and the acoustics are amazing. It's just beautiful. So like they have Christmas caroling, I believe, under this little alcove where it just echoes all throughout it. It sounds amazing. I mean, we have not been there for Christmas, but we're planning on going there for Christmas at some point, listening to either us doing carols or, you know, listening to professionals singing in that space. It's gonna be amazing. Anyway, so Brimham Rocks is just a like rock formation that was put there by glaciers during the last ice age, and the guys who go there do a lot of lead climbing, at least to get their initial ropes up, and then once the ropes are up, they can do top rope. But it's just amazing to watch these guys get up there, because they're doing all sorts of. Not all the routes are terrible or like, you know, high rating or anything like that, but just lead climbing has always kind of freaked me out a little bit. But yeah, Brimham Rocks is one of those places that, like, it's close enough that we could probably go there whenever we want. It's not quite close enough to, like, make it a bike trip or, like, spend an hour, right? If you go there, you're gonna want to spend at least a couple to 3 to 4 hours. Like, spend the morning, bring lunch, or buy lunch at there's a food stand at the top. You don't want to generally go there for a short amount of time, just because we're not that close. But it's great because there's also like smaller rocks that are significantly less risky, provided you are paying attention anyway, and they're not like rainy. It's been rainy once. That was not fun. Freaked everybody out. Yeah, we stayed way away from the edges, but yeah, you can essentially go caving. Like, there's not like caves that you can go 100 yards in or anything like that, but it's just like there's a rock formation that's, you know, 30-40 meters tall. You can get to the first 10 meters or so No, it's not that big. You can get to maybe the first like 5 meters, and there's little caves and pockets and things like that that you can crawl through and squeeze your way through and try to figure out, try to negotiate your way into these spaces. And it's really cool just to, have the kids run around and learn how to responsibly boulder. Like, Daddy, can you spot me? All right, good job. Thank you for calling out a spot. Let's... I think that's what I want. Now I'm kind of cursing myself that I actually gave away my voice into Prima. I mean, technically it wasn't mine, it was the school's, but we weren't even using it anymore, so probably falls to me. In nonlinear differential equations, at some point I want to talk about the three-body problem, because that's really cool. Yeah, I guess. Again, we'll talk about Lorentz attractors. We won't actually probably do a whole lot with them, but... Right, our nonlinear differential equations typically end up leading to chaotic results. Simple systems. Really any nonlinear differential equation, but all right. To anybody who's new here, good evening and welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. Tuesday nights typically are our math streams. We're going to be doing some, in the future Tuesdays, we're going to be doing some interesting stuff, I hope. And I always welcome any questions that anybody has in terms of mathematics, in terms of who am I? What am I doing here? And mathematics type questions, because come on now. Oi. You punk. Grr. Alright, we're going to listen to it again, apparently. At any rate. At some point over the summer, we're going to be doing some classes. So I am going to be hosting a differential equations course. This is ordinary differential equations. There's going to be touching on some partial and nonlinear differential equations as well, as you can see here in the syllabus, probably, provided your resolution is decent. We also have Penn Center, who is going to be doing a complex analysis course as a follow-up to Zach. That is e to the 2i pi. Zach did a real analysis class this past winter, of which I was a part. It was an excellent time. We all got completion certificates at the end of it. Haha. And you could expect very similar outcomes with, certificates drawn in crayon. All right, that is Penn Center is our complex analysis, and then I'm gonna give myself the exact same shout out that got you here in the first place, probably. I do not have a Discord. I may eventually have one, but right now, I actually, for the most part, kind of piggyback off of everybody else's. So, thank you. And we also use Penn Center's Discord as kind of a landing point for all of us. So if you do have any questions, you can go to that one and throw something in our maths chat or maths forum. Anyway. So I hope you're all having a good night. And again, if you have any questions, let me know, especially in terms of mathematics. But anything else you want to chat about? What's the state of education on Twitch or various other things? We'll try and answer best we can. Boo, music quit, boo. Really? Skip tracks. You punk. Can't listen to lo-fi anymore. Oh. Shouldn't be that surprised, I guess. Alright, I will be smarter than this. It's a lot to ask, I know. Nope, not gonna happen. Alright, well. We can suffer. Okay, so if anybody has any questions, please let me know. But otherwise, well, could throw in a couple of problem type things. Or we could look at lean. All right. So anybody who hasn't seen this before, this is Lean Prover, specifically the natural number game. We are trying to essentially use the programming code of Lean in order to help build out the mathematical framework that kind of underpins what we've got for just mathematics in general, but also the idea is that eventually what we're going to do is what some mathematicians who are working on Lean would like to do is give Lean to a neural network or complex neural network, i.e. definitely not an AI system because AI doesn't exist, but what people colloquially will call an AI system, and let it just go on a rampage and try to solve all of mathematics, i.e. try and prove all of mathematics. So ideally, what's going to be done is they're going to tell the system, the rules are given on Lean itself. You know what the syntax is for every single different type of function, and then go off and prove mathematics. So it would probably be trained on natural number game. Be able to prove multiplicative associativity, for example, this right here, and all the rest of it. It would get through all of the mathematics that is here, and then it would be able to say, okay, what can I prove from that, and start building itself out. The idea is that mathematicians and computer scientists will eventually have the computer stumble across something that no human has ever done before. So that would be the goal, eventually. It's going to take a long time, but probably also less than I think. All right, so in order to prove multiplicative associativity, in Lean, this also, the A times B times C just straight across here, is going to be associated on the left-hand side. So it's going to be A times B times C. They just don't write it, which, okay, whatever. Sometimes it's a little frustrating, but as long as we all understand that's what it means, then that's what it means, and everybody's going to be happy. Or at least not ill-contented. Okay, so what we're going to do is we're going to do induction. On variable c. It doesn't really matter which way we go, but with DHD. So what this is going to do is it's going to create two goals. The active goal is going to be the initial condition for the induction. So anybody who's ever done this before, what you basically do is you start with a base case. You say, starting with a particular number, in this case, c is equal to 0, does this relationship hold, where a times b times c is going to be equal to a times b times c. So in this case, we've got rewrite, and we can do this stuff is multiplied on the right-hand side. So we want something that is multiplied by 0. And we want to repeat this. Boo. All right, we need brackets around our argument.
Rating party!
Rating party? Why, it's Don Does Math. Oh. Clearly, I don't know what I'm doing. Right. Oh. This one is the square brackets. And this one is the curly brackets. A. There we go. Oh. Retry. All right. Repeat. How do we do repeat? Harumph. There we go. Well, hi everybody. Those of you who don't know me already, my name is Obi-Wan Pez. This is N Simplex Pachinko. We're doing some math tonight. My pretzel rocks ended up crashing, so whatever. Instead of listening to the same song over and over and over again, we're going to just suffer in silence. It's fine. So, hope you're all having a good night. We were doing some curriculum work on the Differential Equations class that I will be teaching over the summer. It may have been delayed somewhat. Yeah, okay. Yep, sorry. It may have been delayed a little bit, but so I've noticed that it has given me enough time to make it to their stream and start it before it goes off whenever I rate out. So I think that is intentional. Because before it basically like it would do it as soon as we got there, but lately Twitch has been not sending us directly over so that we have time to clear, turn off OBS or whatever we've got going. Because otherwise, we broadcast their stream on our stream, and I think sometimes that gets a little dicey. Not that it matters too much, but nonetheless. Yeah. So anyway, we're doing an induction, trying to do an induction proof of the multiplicative law of association. And so what we've got right now is a times b, parentheses, times c is going to be the same as a times, parentheses, b times c. So we're doing an induction and saying, let's use c as our induction variable, or whatever you want to call it. And so our initial goal is that if c is equal to 0, this is our initial condition, then does our relationship hold? So yes, we get this 0 equals 0 if we repeat this rewrite of do multiplication by 0. So here b times 0 is going to be activated, and a times b times 0 is going to be activated here. That makes the entire left-hand side equal to 0. The right-hand side becomes a times parentheses 0, or just a times 0. And then I tell it to repeat, so it does it again. And here we have a reflexive statement, so we just say RFL. And that moves us on to the second goal. Given our HD statement, that a times b times d is equal to a times parentheses b times d, prove that the successor, so d plus 1 in each of those places, is going to also hold. So in this particular case, we have to multiply out our successor statements and then come up with something that's going to be, equal on both sides, so that we get so that we prove that the induction works. So in this particular case, we're going to say that a times b times successor of d, we're going to rewrite this, you know what, we're going to rewrite, we want that the successor, successor equals add 1. Okay. Now we got all this. Then we want to multiply we'll add. That's distribution. Yes. Repeat, rewrite, we'll add. Okay, so we've got an a times b times d on the left-hand side, and we're going to repeat, rewrite, multiply by 1. So all the 1's end up going away from our statement, and then we're going to rewrite HD. Boo. There we go. Okay, and now the left and the right are identical to each other, so we can reflexive this thing. Woo! Okay. I had said before Dawn came over, that Lean is a mathematical programming language that is trying to help mathematicians kind of organize their thoughts and be able to prove statements that they make and try and test their conjectures and see if it's built on a sturdy ground. The ultimate goal is to feed Lean into an totally not AI system and into some neural network and say, all right, what do you got for us? Prove math. And the goal will be that the computer will eventually figure out all of mathematics from base principles that we have figured out, and then hopefully go further and discover something cool and new that humans have never discovered before. So we'll see. All right, so we're going to leave this world, and we got powers and implications. Let's try implication. This is a very different one. All right, we prove that 2 plus 2 is equal to 4. In implication world, we'll learn how to prove that 2 plus 2 is not equal to 5. In addition world, we proved equalities like x plus y equals y plus x. In this second tutorial, we'll learn some new tactics enabling us to prove implications like x plus 1 equals 4, therefore x equals 3. We'll also learn about 2 new fundamental facts about natural numbers, which Peano introduced as axioms. Okay, so in here we have assuming x plus y equals 37 and 3x plus z equals 42, we have x plus y equals 37. Right, so x, y, and z are going to be natural numbers. H1 is a statement which says x plus y equals 37, and H2 is a statement which says 3x plus z equals 42. The goal is to just state that x plus y equals 37. So we have the statement that we want in the first place. So we just say, well, this is exact. This is exactly the same as the thing we're trying to prove. And we're trying to prove H1. Congratulations. It's terribly difficult. If the goal is not a hypothesis, sometimes we can rewrite to fix things up. So in this particular case, we have an assumption that x plus 0 is equal to y plus 0, 0 plus y plus 2. And the goal is that we have x equals y plus 2. So we want to take this and say, all right, let's, oh, I see. So instead of reversing the add 0, reversing 0 add in order to get zeros on the left of all this stuff, what we're going to say is, okay, let's try and simplify h. So we can say, rewrite 0 add in the statement h. Ugh. Okay. Repeat. Okay, so now x equals y plus 2. And now we got it. So exact h. Congratulations, it works. If x is equal to 37 and we know that x equals 37, that implies that y equals 42. Oh, and we know that x is 37 implies y equals 42. Then we can deduce that y must be equal to 42. So in this is saying that we can use the apply statement to apply one statement h onto another. So y equals 42. Y equals 42 is exact with h1. I was telling everybody a bit earlier about my escapades in choosing the Wensleydale cheese that we had at tourist attraction that we went to. So this Wensleydale is a bit crumbly, it seems, but it is technically a hard cheese, and it's very strong in its flavor. I was not expecting that at all. Thanks to Wallace and Gromit, by the way. Okay. If A and B are numbers, then successive successive injective. AB is a proof that successive A equals successive B implies that A equals B. Use this, click on this theorem in the piano tab for more. Honey lemon, yeah. So I actually did pick up a Wensleydale that was like, I don't know, onion and cranberry or something like that, and I was like, nope. As much as I would like that, nobody else would, guaranteed. So I think my daughter would actually like this pretty well. It was just surprising. What was it? So Wallace and Gromit, my brother and I kind of watched Wallace and Gromit once we found out about it, pretty obsessively. So there's an episode in which Wallace meets a woman, and he asks her about, can I get you some cheese? And she was like, oh, I don't really like cheese. And he's like, well, not even like, and he starts listing off a whole bunch, and she's just like, no. And then he's like, not even Wensleydale? And I was like, oh, come on, we've got to try this. Like, I just came across it. I was like, all right, definitely have to try it. So Wensleydale is, as far as I know, one of the Yorkshire Dales, which are basically, small towns in Yorkshire, typically in the, I want to say, north of Yorkshire, and like the BBC Radio, whenever I hear like an ad break or something like that, it says like this station is serving, X, Y, and Z. So most of the time it says like Yorkshire and the Dales. And I was like, oh, okay. I think I get it. Probably don't get it. It's fine. All right. Piano had this theorem as an axiom, but in the algorithm world, we have to prove it in lean. Yep, okay. So, proceed by manipulating h into the form that we need. So, all right, punk. Oh, at h. That actually makes sense, yes. Okay, yep, right. So combine x plus 1 into successive x. So rewrite successive equals add 1, but this has to be backwards. So we do a /L. Nope, \L. Oh, at h. There we go. And now we apply successive injective at h. A. Or FL. Oh, come on. Oh, no, no, no. No, no, that's not what it is. It's exact. Okay, so we're going to rewrite backwards for equals successive 3. And rewrite successive equals add 1. A. So we have a goal. X equals 37 implies x equals 37. So here we're going to intro h. Okay, so we do intro in order to split the implication. And now it's just the same, so whatever, it's fine. Okay. Alright, so now we can back this off and try to get back to the successive on piano. Successive injective. So we say that we want to repeat, rewrite backwards. Successive equals add 1. Yep. Intro h. Successive x equals successive y implies then the goal x equals y. So yes, we can rewrite successive injective at h. Nope. Successive a equals successive b implies that a equals b. Okay, so if we go back, actually, instead of intro, we potentially just say exact. No, that's not exact. Rewrite successive injective. Oh, come on. A, maybe. Yeah. No, that did not do it. What the hell? x. No. Well, I mean... should not work. Immediate goal solved. Unexpected end of input. Failed attempt, but at the same time, somehow it worked. Hey, there we go. It is the exact successive injective of xy. There we go. Okay, yeah, so they did intro that particular statement. It's probably easier just to use it, but nonetheless. Still can't prove 2 plus 2 does not equal 5, because we haven't talked about the definition of not equals. Oh. Oh, come on. Okay. So apply h to the fact that x does not equal y at h1, where x equals y, and therefore x cannot equal y, which then therefore means h1 is false. All right, 0 is not equal to 1. Let's prove it. Oh. Okay, the fact that 0 equals 1 is false. Makes sense. We're going to rewrite what is 1 equals successive of 0. Oh, no, we wanted that. That's fine. And then this one was... Oh. Ugh. 1 equals successive of 0 at h a apply 0 not equal to successive at h. False. Exact. There we go. Exact h. And we're going the other way, right? Of course, because you can't just prove something one way, you gotta prove it both. Okay, intro, we got this. And then we're just doing the same thing. Rewrite. One equals successive. At h. This is going to be a perpetual problem. Okay, so then sim. Nope. At h. Boo. Okay. Oh, not available in this game. Okay. No, that's fair. I just wasn't reading closely enough. Okay, so rewrite. Piano. Maybe. Yeah. Rewrite. 0 not equal to successive. Boo. Right, it's the wrong way around. We already knew that. You did do it. Whatever. At h. Why? Rewrite failed. Equality or if proof expected. Apply. Nope. Arg. I don't know what to do here. Right? You have... Wait. Does it need a not equal in it? It does. Arg. Because this has an equal in it. Okay. Okay, we did the sim, so it flips it around, and then it just becomes the same as the last one we did. At least I thought, right? 0 equals successive 0. Apply. Oh, is that the problem? Ah. There we go. Maybe. Yeah, no. So it's not apply. It's not that either. Oh, come on. I mean, literally, it's the same one as the last world. So, what happened? 0 equals successive, 0 goal, false. Apply, 0 is not equal to successive at h. It became h is false. No. Oh, is that the problem? There we go. Okay, born to prove in full. Given only the tools we have currently to make it a bit less painful, we gave you unfolded all the numerals for you. Ugh. See if you can use 0 is not equal to successive, and successive injective. Let's see. Can we rewrite the left-hand side? Well, couple last things we can try. Oh, jeez. At A. A, there we go. Jeez. Can we just repeat this? Okay, that's better. Now we can just repeat, apply, piano 1, 0, 0, not equal to successive at A. Boo. Or, yeah, that wasn't it. It wasn't 0. It's not equal to. It's the other one. Successive injective. A. Okay, now we can state the exact thing that's here. Nope. Okay. Not equal to successive at A, right? Yeah, there we go. All right. Exact A. Woo! All right, that is implication and multiplication world done. I think tonight that's gonna about wrap it up for us. So we will go and raid out to somebody we're following. Danny Highways on tonight. Wonderful 101. Blind playthrough. I imagine that is not blindfolded. Heyo. All right. Let's head on over to Astro Canuck, who is doing live astronomy, 3D printed Mandalorian assembly, and Lego Milky Way. Interesting. So, oh, Direnja? Possibly? Oh, you guys are already over there. Yeah, let's do it. I'll probably hit up Astro Connect some other time. Anyway, Hope you all have a good rest of your week. We're gonna head on over to Differential and go see what they're up to on Lean, and I will be back for games, possibly more math later on this week. Depends. Kind of, we are increasing our presence here, so probably don't want to stream every single night, though. My back's going to start killing me. So, hope you all have a good rest of your week. Anyway, my name is Obi-Wan Pez. This is N Simplex Pachinko. Have a good night. See you soon.